Okay, I think we are live. Okay, good. Right. Kind of forgot most of what I read. Yes, day before Monday. Kinda. Oh no, I didn't. I remember some of it. Okay, for today, I'd like to get most of the reading done. For now, anyways. Doesn't look like it. There is a lot of fucking reading. Which is fine, because there's a lot of new stuff. Oh no, okay, there's not that much reading. It's like 2, 3, 4, about 5 or 6 pages. That's fine. That's nothing. Okay, slowly scrolling. Yeah, apologies for the scroll. Not that anyone complained. Alright, it's a bit warm. A bit warm, eh? Okay. Alright, bytecode. What the fuck was that? Okay, bytecode. Virtual machines. Hang on, I need some coffee. Virtual machines execute bytecode. Like the machine code that computers execute, bytecode is made up of instructions that tell the machine what to do. Push this, pop that, add these, call this function. It's called bytecode because, well, those are the things we tell the machine to do. The machine. It's called bytecode because the opcodes contained in each instruction are 1 byte in size. An opcode is the operator part of an instruction, sometimes also called op. Okay. Ah, interesting. I had no idea. Okay. Push that we've seen earlier is such an opcode. Except that in our toy example, it was a multi-byte string. Yes, JavaScript. And not just 1 byte. In a proper implementation, push would just be the name that refers to an opcode, which itself is 1 byte wide. I mean, no, can't blame JavaScript for it. I could have used, I forgot, does JavaScript have enums? I don't know, never mind. Okay, I gotta quickly check enum.js. Yeah, they do. Yeah. Okay. It's an object underneath, so probably, yeah, I don't know. All right, never mind. Don't know where I was going with that one. Anywho, yeah. Yep. Okay, these names like push or pop are called mnemonics. Ne. The M is silent, I'm guessing. Mnemonics. They help us programmers remember and talk about opcodes. literally had no one talk to me about opcodes. Maybe I'm not in the right circles. The operands, also called arguments and parameters to these opcodes, are also contained in the bytecode. They're placed alongside each other with the operands following the opcodes. Okay, the operands though aren't necessarily 1 byte wide, because they can be registers. That would be a memory wide as the memory, or like as wide as, yeah, size of the memory. Oh yeah, it could be a big number. Some opcodes have multiple operands, some just one, and some don't have any at all. Whether the bytecode is designed for a register or a stack machine has a huge influence here. Oh, interesting. Init Bob James. Hello. How you doing? Init Bob James. It's a funny name. I'm good. Well, thank you. Okay. You into compilers and programming? Init Bob James? I think I kind of get what you mean by your name. Just call you Bob. Bob. Oh wow. Okay. You kind of like programming. Bob is great. Okay. But didn't do it for 20 plus years. How come? That's a long year. Oh, yeah. It's a long while. I would say things have changed, Bob, since you've been gone. Hey, that means it's still on the table. You've got the account. Hey, fair enough. How about me? Okay, well, I mean, I've been programming not that long. Maybe 5 years. Yeah. I'm trying to build a compiler. Never built one before. And I thought doing it publicly might be a good idea for some reason. So here I am. And so I'm trying to follow this book. Yeah, and I'm just reading parts of it before I write any code. Before this, I built, I don't know how much, I built Alexa and a parser. So I've done parts of it. Now I need to do the actual compilation. That's where I'm at. Oh yeah, and I'm trying to do it in Zig. Yeah, I know. Yeah, I think I think so. Teach us, sensei. Yeah, no, I wouldn't go that far. like some of the stuff, a little more, a little about Zig. Well, that's quite a broad question. Okay, I mean, Zig is, if you've never used it, or I think you've heard it probably. It's just a low-level programming language, like C. It's a little bit more verbose compared to C. But I do like it. And why do I like it? I don't know. I've just I've just started using it for maybe, or like been programming in it for 6 months. And what my favorite bit so far is the error handling. Might seem verbose for some, but I do like it. I also like Go's error handling, so it's quite similar. Yeah, end of lesson. Have you done any Zig, Bob? Yeah, I also wanted to ask if would you like to get back into programming? Okay. I know, sir. But yeah. Okay. Yeah. It's pretty cool. If you haven't been programming for a while, try it. It's quite fun. Yeah. Why not? Yeah. Talking to Bob. You could be talking to Bob too. Yeah, just go for it, Bob. What's stopping you, if I may ask? You're thinking what's stopping you? Worth the wait. I guess you were thinking if there's anything. Yeah, just go for it, Bob. Well, the good thing is, either way, no one really cares, right? So if it's something you want to do, no reason like not to. And I only like tried this out, like streaming, out of curiosity. I'm very insecure about being in front of camera. Turns out when I'm streaming, not a problem, because I don't have to look at myself. And I can do something while I'm on stream. So I don't have to like focus on me being on camera. And I'm just like a small part of the screen, which is even better. I mean, I could have just left out the camera, but I also wanted to face some of that insecurity. So I left it in. There you go. That's my 1 minute motivation. You're welcome. Okay, you're welcome. And well, I too am trying to just dive in and practice my. Yeah, actually, that is another thing. I realized when I was streaming or started streaming, I was mumbling early on. Don't go back and judge me on it. I was mumbling, so I looked up how to speak more clearly, and I've been using the stream as a practice. As practice. Yeah, so there's that. And I guess also 100%. Oh, okay, here we go. I hope you're ready. Because it's gonna just blow your socks off. Or not. Depends how good the book is written, how well the book is written. Okay. Alright, the operands, also called arguments to parameters or parameters. I'm from India, but I live in Thailand for the last decade. Hey, no, it's fine. I think, well, this is like part of the reason for streaming, right? You wanna, yeah, Thailand's asleep. It's too early. Nice. There's a lot of English people here. Oh, quite a lot. A lot of my friends are English. Well, two of them. Not a lot. Okay. Gonna. I'd love to go swim in the sea right now. Might take you a bit longer. Not sure what's the sea like in Thailand. Oh, it's really good. Oh no, I will. I'll answer the last one. The sea is really good. I used to be a dive instructor for about 4 years, 5 years, 4 or 5, maybe longer. Yeah, maybe longer. Yeah, it's pretty good. The sea is really nice. It's warm, not very cold, and the water is very clear and calm. Yeah. You went diving once, yeah? Said I was a natural, only went 12 meters. Yeah, I think that's as deep as you're allowed to go. I think 12 meters before you get certified, I think. Clear and calm breaths. You're very chill. I love that. Oh, you mean underwater? Yeah. Underwater is pretty chill. It's like being in a different world. But after 5 years, I haven't been back diving at all. Kind of sick of it. Oh, me. Oh, thank you. I appreciate that, Bob. Okay, let's learn a bit about bytecodes, because there's a lot of fucking reading, and I'm kind of sick of it. I want to, start writing some code. Okay, but it's fair. There's a lot that I don't know either, so I understand where the writing's coming from, where all the reading needs to be done. Okay, where was I? They placed, okay, yeah. The operands, also called arguments or parameters to these opcodes, are also contained in the bytecode. They're placed alongside each other with the operands following the opcodes. Make sense? The operands, though, aren't necessarily 1 byte. Okay, I think I read this because you can have big numbers, apparently. Some opcodes have multiple operands, yeah. Whatever the bytecode is designed for, a register or a stack machine. Yeah, okay, I did read this. You can imagine bytecode as a sequence of opcodes and operands laid out in memory next to each other. You can imagine bytecode as a sequence of opcodes. Okay, yeah. Okay. Yeah. Get this? This helps to illustrate the general idea. Bytecode is a binary format and not nearly as readable, meaning that you can't read it like a text file. The mnemonics, like push, don't show up in the actual bytecode. Really? I gotta read that again. Bytecode is a binary format. Right. Okay, yeah, can't read it as a text file. And mnemonics like, okay, I got it. Their representation might, I'm guessing. They are replaced by the opcodes they refer to. Ah, fuck. Okay, now I understand. So the word push is associated with an opcode. That's what the opcode is. Okay. Took me a second. And those are just numbers. Bytes. Which numbers exactly is up to the person defining the bytecode. The push mnemonic might stand for the number 0 and pop might refer to number 23. The operands, yeah, okay. I think that makes a lot more sense. The operands are also encoded, and again, it depends on its value into how many bytes. Yeah. In case it needs multiple bytes, the order in which it's encoded plays a big role. Yeah, because otherwise the number would totally mean something else if you mess up the order. Or is it like, what's it called? The little endian. Yeah. Network byte order and host byte order, something like that. There are 2 possible orders. Hey, it was right here, called little endian and big endian. Little endian means the least significant byte of the original data comes first and is stored in the lowest memory address. Big endian is the opposite. Yeah. Excuse me. I never really remember it. I just called. In C, you have methods. Network to host and host to network. If we, as bytecode designers, were to declare that push refers to 1, add to 2, and integers are stored in big endian, we could encode the example from above and lay it out in memory like this. Right. Push. Okay. I'm just gonna have to take your word for it. What was big endian again? This one. The most significant byte comes first. Okay. Ah, fuck. I just realized. I totally misunderstood the little endian and the big endian. Maybe I still do. Because I thought... No, it isn't. Yeah, I totally misunderstood it. I thought the order of a single byte was flipped. That's not the case at all. Fascinating. How many things I had? That's like 4 things at this point that I thought I knew, which I didn't. Interesting. Okay. What we just did, taking a human readable representation of bytecode and turning it into binary data, it's done by programs called assemblers. Heard of them? Yeah. Assembly language is the most readable version of bytecode. It is, containing mnemonics and readable operands. The assembler turns it into binary bytecode, the reverse, transforming the binary representation into readable representation is done by disassemblers. Never knew they existed. Assembler turns, okay, gotcha. Alright. Yeah. Maybe I can just general statements here. Bytecode is created. Yeah. It doesn't seem that important. Yeah. The bytecode for JVM, for example, contains these instructions. Invoke interface. To invoke an interface method, get static to get a static field of a class. New to create a new object. Ruby's bytecode has put self instruction to load self on the stack. Send a message to an object. Put object to load any object to the stack. And Lua's bytecode has dedicated instructions for accessing and manipulating tables and tuples. You won't find any of that in the instruction set of a general purpose x86 CPU. That is interesting. I had no idea you could do that. Excuse me. That's pretty cool. I like that. I guess it kind of makes sense too. Because otherwise all the languages would be the same. As in underneath. This ability to specialize by using custom bytecode is the biggest reason for building a virtual machine in the first place. Not only do compilation, maintenance, and debugging get easier, but the resulting code is also denser. Because it takes, and makes it faster. Nice. Blah, 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 blah. Okay. I think we're nearly done. Good. I'm a bit tired of all the reading. What we're going to do, or the duality of VM and compiler. Okay, I think this might be useful to have as context. Yeah. Building a virtual machine and a matching compiler requires us to solve a variation of the chicken and egg problem. Which one do we build first? The compiler that outputs bytecode for a machine that doesn't exist yet, or the virtual machine that no one produces any code for? I'm guessing it's going to be a bit of both. I can see it already. We're going to build both at the same time. Makes sense. Because otherwise we're just programming in the ether. Building one completely before the other is frustrating. Okay. It's hard to understand what's going on and what is the purpose of what you're doing. If you're building the compiler and defining the bytecode first, it's tough to make sense of why things are. Yeah, exactly. Yeah. Building the virtual machine before, well, you got nothing to run on it, so I guess that doesn't make sense much. Well, that doesn't make much sense either. It's hard to do without closely looking at the source language constructs the bytecode aims to represent, which means you're going to spell out the compiler anyways. Right. Maybe. Okay. What is the plan? Okay, yeah, that is the goal. Well, that's my goal. The goal is to learn how to build both from the ground up. That's why we're going to start small. We're going to build a tiny virtual machine. Only supports a tiny number of instructions, and a matching tiny compiler only knows how to output these instructions. Perfect. How all the pieces fit together. We'll also have a running system right from the start. Yeah. I'm quite excited for this one. Never built a virtual machine before. To be fair, I didn't know what they were exactly till I read this book, or like this chapter, because I thought they were, well, I don't know what I thought they were. They were not that. They were something else. Yeah, we'll have a run-in system. Also makes the whole journey a lot of fun. I like a fun journey. Now you know what the plan is, and you also know enough about compilers and virtual machines. Right, okay, perfect. Let's go. We're getting there. Chapter 2. I feel like this is turning into sort of a book club. I like it. Don't worry, there's not going to be a lot of reading. Thanks, Bob. You know, it's kind of strange just reading a fucking book on stream. So weird. But I like it. All right. Chapter 2. Hello, bytecode. A goal for this chapter is to compile and execute this expression. Oh, this is just gonna bite me in the back, isn't it? Hey, Bossy, how you doing? The one thing I didn't implement in my parser is the first thing we're going to execute. Might have to go back and do that. Okay, never mind. We'll see. That doesn't sound like an ambitious goal, but in order to reach it, we will have to learn many new things and build up a lot of infrastructure we're going to use in the upcoming chapters. Excuse me. And by choosing the simple expression 1 plus 2, we won't get distracted by the monkey code itself and how it should work. Need some water. Messing with TDD. What are you messing with it for? Right? Are you building something? We'll see. At the end of this chapter, we want to be able to take the monkey expression 1 plus 2, tokenize and parse it. Yep. Yeah. Already done. Take the resulting AST whose nodes are defined. Yeah, they're already there. Pass it to the newly built compiler, which compiles it to bytecode. Take the bytecode and hand it over to the newly built virtual machine, which will execute it. Been watching stuff. I think I will write something tonight. Messing with it to learn. Oh, makes sense. TDD. I'm guessing that is, yeah, it is. Test-driven development. What are you going to develop though? I think it's good practice. Not really. I have to say. Well, as to why, I just don't know what to test, when I start. Because most of the time when I'm doing something, I'm not very good at gauging from the beginning what is supposed to do or what might do. So I find it really hard to think of tests. So I always write them after. I do like tests, but I do write them after. I don't know what to make really. I think testing functions which have side effects. Yeah, see, that makes it even harder to write tests for. Because, I mean, yeah. I have a simple rule that I follow even at work. Yeah, I mean, definitely go for it. I think it's a good practice. Don't let me discourage you. What I like to do is at work, if a bug gets reported, that's when I write the test. Well, we're a small company, so we can like afford to do that. Yeah, because our focus is to like build more stuff. So we only write tests when things break. If that makes sense. But I do write tests when I'm not sure myself. So it's a bit weird. I have like an abstract rule for writing tests. But I think TDD is a good idea. I used to do it a few years ago. I wanted to do the same thing. What was I saying? Okay. Quite bad with source control. So I want to try TDD with... Okay. Yeah, that's an interesting approach. Yeah, I don't know what, but yeah, I think it makes sense. I think it's a good approach. Should definitely try it, like, and then you can make up your mind after. Well, all the time. I tend to commit in chunks. Yeah. I mean, my workflow is not, it's quite what most people do, I think. Usually create a pull request and I just commit things. As soon as I have something working, I commit it and then I only make updates after. And I only do it because there were more than one occasion. You know, like on the terminal you do like Control R or like you do Control P to run the previous command. One time or like few times I think I ran like git restore dot because I wanted to clear some of the changes before. Yeah, and I've shot myself in the foot. Never lost them completely because luckily in Vim it stays in the buffer, so I just pressed undo. But there were a few times where I almost lost a lot of work. So now I commit as soon as I have the smallest thing working. And I do commit often. And what I do is when I merge from a branch back to whatever branch, definitely, I always just squash the commit and I just structure it well. when the work is done. So I have a clean commit history most of the time. And they're all, yeah, it's nothing like fancy. I just do, it seems to work. But yeah, but I would say try it out. Maybe you might find something better. But I wouldn't worry too much about it. Like if it's, as long as you don't lose any work, I think it's fine. That's what it's there for, right? Well, and you don't mess up anyone else's work. Two things. But yeah, try it and let me know. I also want to try because I definitely do forget things at times and also jump the gun. That I overcomplicate something. I used to think the same way too, but I guess sometimes you have to overcomplicate it to know that you've overcomplicated it. Does that make sense? I think it's all part of the experience now. I think forcing myself in smaller steps will be beneficial. Yeah, I think might be. One way to find out was see. Not very long. Maybe 5 years max. What about you, Wasi? How long have you been a programmer? Okay, for me it's about 7 years, and I'm coming to the realization that tests are really important. I'm only discovering this later on though. Guess that's the trade-off with being self-taught. I agree that tests are very important, and I do tend to write them quite often. I think I write more tests now than I did before. Yeah, but only for the things that I'm not sure about. It's like simple functions, I don't really write them. What's in the mug? It's coffee. Black. With a little bit of sweetener. I have also gone in circles many times. If I had tests, I don't think that would have been the case. Maybe. Yeah, I think I would say, yeah, maybe. I like the idea that I can break things and have tests tell me if I did. That is really good though. I think whenever I want to refactor something, what's it called? Yeah, I'd rather have tests than not, because you can just freely refactor and the test will tell you that if you broke something, if you wrote good tests. That is a really good reason to write tests. What does TY mean? Does that mean you leave him, Bob? Oh, okay. Okay. Thank you, Bob. Yeah, we'll see. I think tests overall, big, yeah. Like big. I find, well, whatever. Big something. Advantage. Especially when you want to change stuff, which is quite often. Yeah, try it and let me know how it goes. I become dogmatic towards things, but when I do that, I learn better. Oh, I think that's a good approach. Yeah, I think you gotta, if you do want to like really learn something, I do feel the best way is to just go all in, and then you can make a proper opinion on it, have a proper opinion on it. I wasn't like trying to be discouraging. I think you should definitely try it. No, don't worry. I don't mind it really. It's a nice break. Oh, yeah. I've still got it. Let me check. Yeah. Nothing. Like, it's, I like it. I like that I put it back. Well, I have got the hard time thing because it made me realize how much I use it. And it's forcing me to like think about what I'm doing. And it's like, it's bought new, what's like a new something, new wave of curiosity to get better at Vim. Because I think after the first 6 months, I don't think I kept learning. It resets, yeah. I think not by default. I had to, because I do use relative numbers quite often. And then it was, what's it called? It didn't reset. But yeah, it's pretty cool. I like it. I think it's a step in the right direction. I think the only config I changed was that to reset when I use count. Time for me to think of a simple learning project. Yeah. Oh, I think I just had an idea. The first one could be something you've already done before. So might be easier to start, thinking of tests. So you start off with like level 0 and then you try something you don't know. That makes sense. All right. Anyway, good luck with your project. I'm going to continue reading because I've got a little bit more. And then I can, excuse me. Yeah. And I think for the first one, it's like a good practice. You can like just send me a message whenever. I'll read it. That doesn't sound, yeah, 1 plus 2 compiler and virtual machine. All right, cheers, Bossy. At the end of this chapter, we want to be able to take the monkey expression, tokenize, and yeah, I think I read all of this. The 1 plus 2 expression will travel through all the major parts of our new interpreter. Lexer, parser, compiler, virtual machine. Okay, got like here. In terms of data structures, you can see that there will be quite a few transformations until we end up with 3 as our result. String, tokens, ASD, bytecode, objects. Right. Since we'll be using a lot of packages we built in the previous book, we can already handle everything up to the AST. After that, we're entering uncharted territory. Yeah, after, yeah, we need to define bytecode instructions. Build a compiler and construct a virtual machine. Just to turn 1 plus 2 into 3. Sounds daunting? Sounds exciting actually. We'll do this step by step and build from the ground up as always, and start with bytecode. First instructions, finally. Oh, coffee noises. As I mentioned in the previous chapter, the architecture of the virtual machine is the single biggest influence on what the bytecode looks like. That means we need to decide what type of machine we're going to build before we can start to specify bytecode. So without further ado, let's pull back the curtain. We're going to build a stack machine. Why? Because stack machines are far easier to understand and build for beginners than register machines. Less concepts, less moving parts. Well, that could be part 2. After I build the compiler, well, a stack machine, you're going to build a register machine. Sounds like a good idea. And all the performance considerations. So the register machine faster do not play a huge role for us. Right. Later on, we'll see more of the implications this decision has, but the immediate and most practical one is that we now have to do stack arithmetic. That's not too hard, is it? That means in order to reach our declared goal of compiling and executing the monkey expression 1 plus 2, we have to translate it to bytecode instructions that make use of a stack. Right. The stack is where the stack machine does its work, and we can't just tell it to add 2 numbers. without making use of the stack. Okay. Excuse me. Thankfully, we saw a similar example before and already know how to do arithmetic with a stack. We first get the operands 1 and 2 onto the stack and then tell the VM add these. This add these instruction should then cause the VM to take the two topmost elements from the stack, add them together and push the result back onto the stack. Yeah. So in order to fully implement this, we need to tell the VM push 1, push 2, add the two topmost elements together. So we need to create three instructions. As programmers though, we know that we only need to define two separate instruction types, since pushing 2 onto the stack should be the same as pushing 1, except that the argument is different. So 2 instruction types in total, 1 for pushing and 1 for adding. First we define their opcodes and how they are encoded in bytecode. Then we extend the compiler so it can produce these instructions. As soon as the compiler knows how to do that, we can create the VM that decodes and executes them. And we start with the instructions that tell the VM to push something onto the stack. Yep. Okay, kinda. Okay, is that a lot of text? Because I'm thinking I can start this tomorrow. What else have I got? Okay, I think I want to do like most of the reading done so I can start programming tomorrow. But doesn't, yeah, I think that seems doable. Yeah. Okay. Fuck, where was I? Right here. Okay, let me read a little bit more so I can start programming tomorrow. Here we are. We need to define our first bytecode instruction. How do we do that? Well, since creating definitions while programming is not much more than telling the computer what we know, let's ask ourselves, what do we know about bytecode? What do we know? Well, we know how big it is. Bytecode. Bytecode. Turns out not much. You tell me. We know that's made of instructions. Okay, yeah, we do. Oh yeah, it's got a something in bit before, like an opcode, probably a number or an enum. And then it's followed by what to do the action on, kind of. We also know that the instructions themselves are a series of bytes. Oh, the question would be, how do we know when, one bytecode has been executed and it's the next one? Not sure. And an optional number of operands. An opcode is exactly 1 byte wide. Yeah. And has an arbitrary but unique value and is the first byte in the instruction. That kind of makes it like harder. Maybe it's separated by something. Let's have a look. Exactly 1 byte wide, unique, has an arbitrary but unique value and is the first byte in the instruction. Looks like we know quite a lot, and the best thing is that this is precise enough to be turned into code, literally. It's our first official practical act of coding in this book. We create a new package called code. We start to define our bytecode format. Opcode is a byte and instructions are slice of byte. Perfect. Yeah. There are two definitions missing here. What might they be? First one is instruction, singular. Why didn't we define it as... Why didn't we define it here as slice of byte? Because it's far more handy to pass around and work with a slice of byte and treat it implicitly as an instruction than to encode this definition in Go's type system. Okay, yeah. I mean, why create instructions? That makes sense. We've seen enough know how we're going to use slice of byte and how cumbersome type assertions and typecasting from and to an instruction type would be there. Actually, even now. But I'm guessing he'll define methods that would allow you to do it. The other missing definition is one for bytecode. there should at least be some definition of bytecode that tells us it's made of instructions. Bytecode is made of instructions. The reason for its absence is we'd run into a nasty import cycle. We were to define bytecode here in the code package. Once we get to the compiler, we'll define it there in the compiler's package. Okay. Now that we have definitions for opcode and instructions, we can define our first opcode, the one that tells the VM to push something onto the stack. And here's a surprise. The opcode won't have a push in its name. In fact, it won't be solely about pushing things. Allow me to explain. Please do. We said earlier that when we compile the monkey expression 1 plus 2, we want to generate 3 different instructions. Yeah, push, and then add. 2 of which tell the VM to push 1 and 2 onto the stack. First instinct might tell us to implement these by defining a push instruction with an integer as its operand, with the idea being that the VM then takes the integer, pushes it back onto the stack, and for the integers that will work fine. You could easily encode them and put them directly into bytecode. Yeah, that was my next question. But what if we wanted to push string literals, for example? Yeah, you can also put them, but how would you know if it's a string? It will sooner or later become unwieldy. That's where the idea of constants come into play. In this context, constant is short for constant expression and refers to expressions whose value doesn't change. Is constant and can be determined at compile time. Interesting. That means we don't need to run the program to know what these expressions evaluate to. A compiler can find them in the code and store the value they evaluate to. After that, it can directly reference the constants in the instructions it generates, instead of embedding the values directly in them. And while reference sounds like a special data type, it's far easier than that. Plain integer does the job just fine. It can serve as an index, all constants, like a constant pool. Okay. And that's exactly what our compiler is going to do. When we come across an integer, literal, constant expression, while compiling, actually, yeah, they are constants. Because if I look at, so in all of these tests, no, but that means, yeah, they do. They all evaluate to constituate. Fascinating. Okay. So to my screen. Oh. Right. We'll evaluate it and keep track of resulting object.integer in memory and assigning it a number. In the bytecode instructions, we'll refer to object.integer by this number. After we're done compiling and pass the instructions to the VM for execution, we'll also hand over all the constants we found by putting them in a data structure, our constant pool, where the number that has been assigned to each constant can be used as an index to retrieve it. Not entirely sure about this pool. Excuse me, my chair's sinking. Might be. It's called opconstant. It has one operand, the number we previously assigned to the constant. When the VM executes opconstant, it retrieves the constant using the operand as an index and pushes it onto the stack. I don't know. I'm like a bit confused. What do you do with it again? Okay, anyway, I think I'm losing comprehension a little bit, so I'll continue this tomorrow. Plus, I'm tired of all the reading. But at least most of the reading's done. Thank you, Bob. Yeah. And yes, can start programming tomorrow. I'm looking forward to that one. And all right, thank you guys. Thank you for hanging out, and hope you have a great day tomorrow or today, depending time of the day. Cheers, Bob. And I shall see you tomorrow, if you're here.